Hi guys, this is Mohammed Sheikh. Now I was going to explain Big Data Analytics and Applications ICP 10. Well, let me share my screen. So the main objective of this ICP is I need to implement the deep Q learning in Python using Keras and OpenAI Gym libraries. So the idea of this ICP, there will be a cartpole, so where the pole will be on the top of the cart. So here what the actual goal is, I need to balance the pole from collapsing by moving the cart side by side. So this can be implemented by using the deep Q learning network, using, as I said, the Keras and the Gym libraries. And then finally we need to visualize our results. So let me share the actual code here. So firstly, what I will be doing, I will be importing the library, as I mentioned, the Open Artificial Intelligence Gym library will be using here. So I was importing the Gym library, and then NumPy as in NP, the pandas library here we will be using. So here, as I said, OpenAI Gym will be having the different modules here, like the carpool is one of the module, and then the taxi is another module. So from the Gym library, I will be using the cartpole v1 environment. So that will be taken into the environment variable. And then so next what I will be doing is in the cartpool environment, we can see there is a cart on the pole on the top of the cart. So I need to balance that pole, as I said. So here the actual for the cart pole environment, you can see there will be 4 observations, like first the position of the cart, and then velocity of the cart, like speed, how it will be moving for one step, either it's a left or right, and then the angular position of the pole, how it is balancing the pole which is present on the top of the cart, and then the speed of the pole. So there will be 4 observations. I mean, there are 4 states in this environment for the cartpole. Then next is the action. So here, the action in the cartpole is, to balance it, it will be moving left or right. So based on that, you can say when it moves left, it is considered as 0. When it moves right, it is considered as 1. And then so you can get, for every movement, for every action, you'll be getting like rewards. Like, so for every step, the model will be trained. So for every step, it will be rewarded as +1, and also for each termination it will be also be getting +1 reward. So here you can see I was resetting the entire environment to a new random state. So this is the function action space sample I will be taking into action variable. So here you can see I'm printing the variables. State space is nothing but it is the default value. So as I said, for the state will be have 4 observations will be having. So for this environment, these are the 4 states, and then the default one for these, the default actions will be having to write either 0 or 1, most left or right. It is 2. And then when after I reset the environment, so I got these values. So initially, in the initial state will be like these 4 observations, and then the initial action is 1. So it will be as I said, in 1 minute it will be moving to right side. And then next, what we'll be doing, so we will be implementing the DQN. So we'll be performing the model here. So actually what the model does is, here the idea is simple, like it will predict the q value for the entire state from the sample state, and also by using the q value data. So so how it will be trained, it will predict the q value here from each observation and then action. So here you can see we'll be designing the we'll be implementing three layers here, as you can see. So 3 layers here we will be implementing. And then so firstly what we'll be doing, the libraries what we will be using, TensorFlow will be importing here. And then, as I said, we'll be taking the observation shape, the observation is 4, and then action size equal to 2. And then we'll be using the layers. So 3 layer hidden layers we'll be using. And then so as I said, the input for this one is like a state. So what the state here, it is 4. So these are the observations, and what the output will be getting, it is a q value. So state, the observation is the input will be giving, and then the q value will be getting is a target. So and then here the activation is using where value which reduces the non-linearity. and then the 3 layers will be given to the model, and then finally I will be compiling the model with optimize losses emission optimizer. We will be using as Adam. So this is the basic steps what we will be doing in training them before training the model. And then next, what here we already know that agent, what the agent will do, it collects for every action, for every action and movement it takes, it collects the data and it will store the data in the queue. It will store the queue values. Then the next, the memory is nothing but so whatever the data is collected through the agent from this queue learning, it is stored in the memory in the form of, like here you can see the state, action, reward, and the next state what it is going to perform. So in this sequence, the memory, the data will be stored in this memory, and replay is nothing but after completing each episode. So how many times so how many times the cartpole is moving, so how many times you'll be giving the based on the episode value. So the data stored in the memory will be taken into a random or mini batch, and then finally it will be trained. So here you can see so whatever the necessary libraries we'll be using will be imported here, and then and then we'll be giving the episode size as 100. It depends, we can give that 1500 2000 like that, but it will take more time for the model to be trained here. So for now I had taken 100, and then memory is nothing but stores the data. So this is the hyperparameters I used: gamma, epsilon, batch size. and then and then I was by using the for loop. So my range is nothing but it iterates 100 times. So as I take an episode size 100, so I will be environment reset. I will be getting the state value. The observation is 4. We got it, and then while condition here, depending upon the epsilon value, and then a random uniform function, the model will act like it, whether it explore or it need to be exploit. So depending upon the epsilon value, it performs the it performs, and then finally these whatever the result we'll be getting, it will be taken into the these variables, and finally we'll appending that variables inside the memory. And then as I discussed, the next, the replay function will be performed, and then so here depending upon the values, so finally the q value will be calculated, and then either it will be stored in the inside the memory, or based on the observations it will update the q value. Finally we'll be closing the environment. So here for 10, so episode for 100 iterations we got, like it took nearly 30 minutes, 28 minutes, sorry. And then for next one, what we'll be doing, we'll be saving our model. So here you can see it's saving the model, and next what we need to is we need to predict the q value from each action using that stored model. So, and also what we can do is we need to visualize the results, like whatever the prediction we got in. So what we'll be doing, I will be showing it as a video format. So before doing that, actually I got one challenge in this ICP, like I was unable to execute environment.render function. So to overcome this one, I had to do a couple of research, like through the browsing I came to know that we need to after adding some of the necessary libraries, I need to execute that render function. So these are the necessary libraries one I had installed in my collab, like install gym virtual displays the library, and then also python opengl. This is the other library. So and then to visualize our video, as I said, I will be showing the form of a video, right? I have to visualize the behavior, I will be showing the form of a video. So this is the gym wrappers and necessary labels what will be using. I had imported, and then this is the show video. This is the function where the exact behavior of the cartpole for the predicted one can be shown. And then finally, what I'll be doing, I'll be importing my saved model from the by importing the TensorFlow Keras model. And then through this load model, I was importing the exact model whatever I had done here. So I will be importing to show to visualize in the form of video. And then finally, so here, so what are the predictions we got, like state and the behavior, the observations we get here, it will be taken into Q table, and then we will be appending, and then finally we'll be calling that video function whatever we had defined. So yeah, you can see this is the video function we define. The behavior, it will be shown in the form of a video, and then finally I will be calling that function by taking whatever the observations we predicted, the state value, the Q values, and then finally I will be displaying the result here. So here you can see, so here you can actually, this should be moving. So, actually this should be moved smoothly, but actually what happened, yeah, this model I executed 2 3 hours before, so that's why it is not moving. So if I need to execute it again, if I execute it, then it will tilt side by side, so it will not be smooth. So if I need to execute it again, it takes again 30 minutes. So actually what here, it will be tilting. So finally, so here you can see, to get smooth, so here in the episode size we had given 100, right? So instead we can, instead of that we can give like 500,000, but it takes more time and it will be viewed clearly. So if you have more time, you can give like for 100 episodes to 30 minutes, and for 1000 it will for 1000 it will take 1 hour or 2 hours, like that, depends. Thank you. Actually I thought to show here.